And now I'm going to talk about a competition. This one just finished a week ago, and it's called the Visual Relationship Challenge. In this talk, I'll give a little overview of the competition, what it's trying to do. I'll talk about the data. I'll talk about how it's evaluated. I'll talk about some of the algorithms and models that people used in their submissions. So what is this competition? So this was the second part of a two-part competition, the AI Open Images competition. The first part was simple object characterization. Given a picture, what things are in it? Give us the bounding boxes of all of the things that your model recognizes, and a label of what you think the object is. So in this picture here, it might detect person twice, guitar twice, human hand 4 times, human eye twice, 4 times, human ear twice, chair, etc. I'm not going to talk about that competition much. Just assume that we can detect objects. The second part makes use of object detection to determine relationships between objects, like to recognize not just that there's a person and a guitar, but that there is a person playing a guitar. So verbs. Whoa. This competition was sponsored by Google, who gave prizes to the first 3 teams with about $10,000 to the winning team. Teams had just under 2 months to complete it, and it ended a week ago. This is kind of normal, the time frame, about 2 months. It's about what they generally take. They generally don't take years, they generally don't take days. Somewhere in a small number of months. This is kind of normal, but the results are going to get presented at the European Conference on Computer Vision next week. And that is kind of unusual and kind of cool. Interestingly, there were some big differences between part 1 and part 2 of this competition. There were 232 teams in part 2 as opposed to 454 in the first part. So there's a significant drop-off from part 1 to part 2. The scores were higher in part 1 than in part 2, and they were much more tightly bunched. So there's a 3%, the spread of the top 5 teams for part 1 was about 3% of the total of the best score, whereas in part 1, whereas in part 2, it was more like 30% of the top 5 spread was like 30% of the best score. The evaluation criteria were different, yes, but they were in the same basic ballpark. They were the same kind of evaluation, so I don't think it was just the evaluation. But I think the reason why there's such a big difference between and also note that there were 8 people who entered solo in the second part. Well, only 8 of the top 10 teams were one-person teams in the second part, but only 2 in the first part. So why is this so different? And I think this partly because object detection is a much more well-understood problem. It's easier to do object detection in some sense. We've been doing this for a while. We kind of know how to do it. It's not a solved problem completely. There's still room to work on it, but we're getting pretty good at it. That means that for the first competition, the way that you won was by eking out that last little bit, so you had to brute force it to try a whole bunch of things and ensemble them together, basically collect them all together. And one way of combining them is to vote. But you combine all of those together, and that will get you a little bit more. If you're going to brute force an attack, a competition like that, it helps if you have a lot of brutes to apply a lot of force. And so the teams that were rewarded were ones that had a lot of people who could work on a lot of different things. The part 2 competition was something that we don't know quite as much how to do. So it had the scores that were lower, and what was important was people just trying different things, I think. So the moral of the story here is if you're new to Kaggle and you're working by yourself, try a harder competition, not an easier competition. This is somewhat counterintuitive, but try a harder one because there will be more room. Or do you keep looking like you want to say something?
Yeah, I want to ask. So by the sounds of it, it's part 2, relationship detection. Is that detection, DET?
Sorry?
Is that relationship detection?
Yes.
Yeah. Seems like that's much more impressive in this case. Do you know if any of those solo teams in part 2 participated in part 1? And do you know if they did well? Because I'd be much more impressed by their approach.
I didn't look for this, so I can't say for sure, but I didn't recognize any names in the top 10 of part 1 that were in the top 10 in part 2. But like I said, I wasn't particularly looking. Any other? Okay. So let's talk about the data for a minute. The competition looked at 10 different relationships. One of the relationships is, which really means is made of, and takes one noun and one adjective. So guitar is wood, chair is plastic, etc. The other relationships need 2 nouns. So chair at table, meaning the chair is near the table. Hat on chair, hat on table. Person holds flower. Dog plays piano. Cat inside of box. So the relationship types are is, at, on, holds, plays, interacts with, wears, inside of, under, and hits. So this means that they have a concept of triplets. Object 1, object 2, and the relationship between them. Except for is, the object 2 is actually an attribute. It's a material like plastic or leather or wood. So there's a huge number of possible triplets. But for this competition, they limited the types of triples which they cared about. For example, the triple of guitar is leather or fork on squirrel probably are not ones that you see very often, not ones that you care about. So they came up with a list of the triples that they were going to score, that they were see. And when they distributed the data, they distributed it in 9 different files, which oddly you have to download from a different site. And it actually took me a long time to figure out where those files were because it was kind of small print over in the corner saying, these you got over there. The most important one is one which gives the image ID, the label for the first object, 4 corners of the bounding box for the first object, label for the second object, 4 corners of the bounding box for the second object, and the relationship between object 1 and object 2. Sorry?
I think that you are talking about the other slide, no? This is the right slide that you are talking?
Yeah, 9 files.
I have a question.
Yeah.
375,000 relationships and 100,000 images. So
Yes.
that means some images have multiple relationships.
Correct.
If it's like man holds guitar, would that just be like man's hold guitar and also man plays guitar and also man interacts guitar?
You might, or you could imagine a picture that had a man playing a guitar and a woman playing a guitar and a cat sitting on a chair watching them and a fork dropped on the ground underneath the chair. You could have a whole bunch of things. And in the submissions file, I'll get to this later, but in the submission file you give the picture ID, and then you give sequences of triplets. You say, man plays guitar, man holds guitar, woman plays guitar, woman holds guitar, cat on chair, fork under chair, and you just continue. And they expect you to have really long strings of triples, which you'll see in a minute.
And for the valid triplets, do they tell you what the valid triplets are?
Yes, one of these files tells you which triplets are valid.
Okay, how many of those are there?
I think it's like 329, something like that. It's 300 or 400.
Oh, okay.
Instead of, 10 factorial.
Yeah.
So it's, oh, here we go. There are 329 valid triplets involving only 62 different object classes. So the first file that's the most, yeah, mode.
How does a triplet look like? Is it a very specific word and then relationship and another very specific word?
Yeah,
or is it a class of words, the relationship class of words?
No, it's the exact format of this file that I just talked about, which gives you the information for the training data, is file ID, which is the name of the file with the JPEG stripped from it. And then it's this code, which is kind of yucky. It's something like M/1062 or 106B. And then it's the 4 bounding box corners. And then it's another label ID like M/Z692, then 4 bounding box, sorry, I'm supposed to stay in front of it, 4 bounding box corners, and then the word is, or at, or on, or holds, or plays, or interacts. But the labels are these gross IDs, and there is a CSV file which converts labels, which has a mapping of labels to English. So you'll see that MZ602 is actually fork, and M/102B is actually woman. Yes?
Question from the live stream. In this data set, the input is all images?
Yes. Well, it's images plus these CSV files, which tell you what the images look like and what the bounding boxes are. But yeah, in the test set, it's all images. Did you say test? Whatever. Yeah. So the training data set has images plus these CSV files, and the test set is just purely images, and you need to give a submission which has essentially the same thing as the CSV file I just described, but you put the confidence you have in your prediction right ahead of each triplet. Yeah.
Sorry, which one of those like a relationship are confusing with each other? So like if the recognition like detect a man and a guitar, okay, it probably said man play guitar. It's not like I said man is guitar, right? Like I'm saying like these relationship types doesn't look like a very like confused with each other.
True. There's a couple of different things that you could have that would be confusing. One is the order. You want to make sure that your model says cat under table and not cat on table if it's under the table and not on the table. Table under cat or cat under table. Those are two very different things. And you want to get that right, although as it turns out, if you have cat table and under, you're going to get some points, even if you have it backwards. And one of the things that you have to do is you have to do the detection yourself. I've been kind of downplaying that because it's sort of easy. I mean, not easy, but that's not the hardest part. So you still have to recognize that that's a cat and not a dog that's sitting under the table. Does that answer your question?
Solid, yeah.
Okay.
So does it differentiate between, say, like cat on table and table under cat?
Where's the mic? Just for the recording audience.
I was wondering if they differ.
On the bottom, under.
I was wondering if they differentiate at all between like cat on table and table under cat, for instance.
I don't know. It may well be that they've listed both relationships as being visible in that image, but I don't know. I did not look at the data in that level of detail. Okay, so I mentioned the one class, which is important, which gives the triples for an image, one per triplet. There's also the CSV, which maps the ID to a human understandable term. You don't actually need this to do the competition, but it's helpful for debugging. You go, why is this not working? And if it just tells you that M692 holds M693, then maybe you can't figure this out. But if you translate it so that it says fork holds cat, and you say, well, that's not a fork, that's a human. Oh, I've got a problem with my object detection. So it's useful for debugging. Then the other files are there mostly to help with object detection, which, like I said, I think is more of a solved problem, so I'm not gonna talk about that. It's clearly important here too, but it's not as interesting for this talk. Okay, then the question of how does your submission get evaluated? Well, glad you asked. Okay. It's actually kind of complicated if you haven't seen this before, and I hadn't. So they do a weighted mean of 3 metrics. Remember I said that when I was showing the difference between the first part and the second part, the object detection and the object relationship detection, how they were sort of similar? For the object detection, they just used this one, the weighted average precision on relationship. But all of these are kind of the same order of magnitude, so they're gonna end up being kind of the same. All right, so what is the mean average precision on relationships detection? Okay, precision is, hello, there we go. Precision is the number of correct guesses versus all of your guesses, divided by all of your guesses. So how many of your guesses were correct? Recall is the correct guesses over all correct answers. So how many of the correct answers did you get right? Now, I need to describe precision and recall in order to be able to describe the mean average precision on relationships, which is their term. It's not my term, it's their term. So precision and recall, you can see, you can calculate easily if it's binary, if there's a correct guess or an incorrect guess. Great. Yeah, but what do you do if it's a probability? If you say that it's 0.7% likely to be correct, then what do? Well, you end up getting, you can still deal with it if you make it a curve. If you say, all right, everything with 0.5, count that as a yes. Then you can calculate the precision for 0.5. If you say everything with confidence 0.7 is a yes, then you can calculate a precision at that point. So you can calculate a curve of precision versus confidence for your data set. You can do the same thing with recall. So now you've got two curves. All right, the mean average precision chops up the recall. It gets 11 different levels of recall, and then figures out what the precision is at that same point in the space, and averages those 11. So you're kind of probably going, huh? See, basically it's averaging. It's doing an average of the precision. One slight difference is that if you're, where's my cursor? There's my cursor. If the intersection over union of the submitted bounding box with the ground truth bounding box is under 0.5, then it just says, oh, that's an error. So this is a modification of the mean average precision that's used in other competitions. So intersection over union is basically a measure of how much does it overlap. So if you've got two things that are, two squares that are rectangles that are overlapping like this overlap area is the intersection, and the union is the sum of the area of the two different squares. So the intersection over the union will be 1 if they are completely the same, and they'll be 0 if they're completely different. Okay? So they throw it out, they say you got it wrong if your bounding boxes are not properly overlapping. Okay, so that was the first one. The second one is a bit more forgiving. It's called recall at n. It looks at the first 50 triplets for an image ordered by score. And they didn't say what score was. I'm presuming they mean probability, the probability that you gave. So if one of those 50 is correct, it will mark the image as correct. So maybe what thing you do if there's the cat on table or table under cat problem is you give both. You say cat on table and table under cat, and you just keep going. So clearly they're thinking that you're going to have a lot of different triplets in your submission, or they wouldn't be saying they look at the first 50. So.
Could it be that you just give a probability for every single possible triplet?
Sure. You would not get penalized at all on recall at 50 for doing that. And there's only 329 of them. So yeah, it'd be a long line, but it wouldn't be infinite. And when I was looking through the descriptions of submissions by some of the finishers, they were saying that this one also does not penalize incorrect guesses heavily. And I looked at this and I crossed my eyes and I haven't figured out yet why that would be. But more than one person said that, so it's probably true. Kenneth?
Yeah, I have some issues with this recall curve. What's 11? You're splitting it into 11. Is it the classes or what?
No, it's the level. So you're going to have a curve for the recall.
Okay.
And, well, you're going to have a curve, and maybe I've got it backwards. They say that it goes from 0 to 1, and so you pick the level of recall that's the y-axis of the recall is want to take recall levels of 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1, and 0. So that's 11 levels. And that will give you an intercept that's at different places. If it were a straight 45-degree angle, then they'd be the same, but it's not. And so you have a probability that that corresponds to that point of the recall. And then you take that point, and then you go look up on the precision curve where it is, where the precision is. Does that make sense? Okay. Okay, so they said this one doesn't penalize wrong scores much. This one clearly doesn't penalize particularly badly, doesn't penalize low probability. Sorry, I should say, it's not that I spoke incorrectly. It's not that it doesn't penalize incorrect scores, it doesn't penalize low probability guesses very much. And this one clearly doesn't penalize low probability guesses much. And then this third one, it's very similar to the first one, but what it does is it takes your two boxes, two bounding boxes for your two objects, makes one big box that holds both of them, attaches both of the labels to that, and then compares it to their big box and two labels. They do the same thing on theirs, two big box, two labels. So effectively what you're doing is you're taking out the order of it. So cat under table and table under cat would look identical for this one. And this one's weighted 0.4, the second one was weighted 0.2, and the first one was weighted 0.4. So it looks to me like it's kind of forgiving. If you're close, you're going to get some points out of it. And so that seems like it would suggest that you should try and guess if you are uncertain. Now, something that I couldn't figure out from the evaluation was hierarchy. So the classes have a hierarchy. Cat is a kind of animal. But they didn't say how they scored it if you said animal on table instead of cat on table. So I'm sorry, I couldn't figure that out. It seems kind of important. Okay, and now I'm going to talk about how different people approached the problem. There were a lot of different write-ups. The 2nd, 4th, 5th, 7th, 8th, and 45th all had write-ups of how they did it. But they were all kind of brief. So I'll talk about each one of them, but it might be relatively brief on all of them. I'll try and talk about commonalities here. One thing that kind of everybody did was they spent some time merging together those 9 input files.
I think you can combine them some other way. Just, I don't even think you need to stack them together. You can just have them work completely independently from each other, and you can just add on the merging. Yeah, it's kind of merging. I don't know. It's awesome. Yeah, I'm not sure. I'm not sure what you would call it.
When you talk about this relationship, is this a relationship between two objects in the same image? That is an example of it.
Sorry, I didn't hear you, but the interrelationship is really made of, so, chair is plastic. Sorry?
Did I repeat the question?
Yeah, I don't.
When you're talking about is relationship, is it a relationship between two objects in the same image?
No, it's an object. It's an object and an adjective. Really, it's made of. So it's very different in some ways. We say object 1 and object. I have been saying object 1 and object 2, and the write-ups say object 1 and object 2. But object 2 isn't always an object.
What is an example of?
Chair is plastic. Hat is fabric. Table is wood. Let's pretend. Bottle is plastic. So made of, really. You just turn it off and set it down. Okay, so we have established that we don't know what this is called, but somehow they combine the output of the is model with the everything else model. There were some features that kind of everybody dealt with. Everybody looked at the intersection over union. Kind of everybody looked at the bounding box absolute size and relative size. Bounding box absolute distance and relative distance to the other bounding box. And the image as an output feeding into the next level of model. Maybe it's called stacking. Is that the right word?
I'm just thinking about this in my head right now, and I'm having a hard time imagining how this would work without a softmax final layer, which maybe you would need a prediction for all of your classes, essentially, and then you softmax that. So you are getting a prediction for everything, and if one model is giving you a prediction for all of the is relationship predictions, then that is just kind of one part of your total output, and then the other model handles the other part of your total output. So they're kind of just combined in a way at the end. They're just separate models, essentially. They're not really interacting. But I don't know if that's true. I don't know if there's a softmax final. So that's the biggest one.
They have to interact somehow, because this model says, yeah, I think that with a 60% confidence, the cherry is made of wood. And you have something else that says, yeah, with 50% confidence, the cat is on the chair. Now, what do? Maybe you just pass both of them through?
Actually, now softmax doesn't make sense because it's a multi-label task.
Yeah.
Yeah. Yeah. Don't know. Anybody have any ideas? What to do in a multi-label sense? You can have each prediction go through a sigmoid, and then you essentially just have a yes or no for every single possibility. The table is wood, has a 60% chance of being true. The table is plastic, has a 50% chance of being true. They don't need to, those two predictions don't need to interact.
That's true.
So maybe that's what it is. And then you just threshold that prediction to say, yes, this is a prediction, or no.
And maybe you don't bother thresholding because the probability guesses are not penalized
the score will,
as much.
yeah, you wouldn't threshold, you would just give your probability for each of them, and then in the scoring metric, when it's calculating the precision and recall, it needs to know if yes you predicted it or no you didn't predict it. So in that recall and precision calculation, it goes through 11 different thresholds. I think that's what it is, and then that's how you give your score. Okay, this kind of makes sense.
Ken?
Yeah, I have a question. How do you implement the loss function for this to be differentiable? Did anyone release an example of that?
No, none of them gave an example of what to use for the loss function. I suspect that everyone did YOLO for the detection part of it. YOLO is, for those of you who don't know, YOLO is an algorithm called You Only Look Once, and it's a way of using a neural net to do object detection in a fast way by being clever about what your evaluation function is. Basically, someone else can challenge me on that. But it's a very common, very popular technique, and I wouldn't expect that everyone would do that. Submission number 2 is the only one who actually says YOLO in their write-up. And so I don't know if the others were doing YOLO or not, but submission number 2 definitely was. And submission number 2 dealt with the unbalanced classes by putting class weighting into YOLO. Now, again, I don't know exactly what they did, exactly how this class rating went in, but submission number 2 was the only one who said that they did that, who dealt with it in that manner. Submission number 4, I thought it was cool how this one did it. They said there's only 42 distinct is triplets that involve the named of relationship. So he just made a separate class for each of the is triplets. And then he trained on that. And he used RetNet, and he did it for both is and non-is models. Now I don't remember what I meant here. So he got confidence for 1 box for top 100 boxes. Oh, he calculated the confidence for the top 100 boxes in his model. In the image. So he'd go and he'd find 100 things in the picture, and then he would use LightGBM to calculate the confidence of the combination of 2 of those boxes. So I think there's a cat with 70% probability, and I think there's a table with 4% probability, and I think there's a guitar with 80% probability, and then he would figure out how likely it was that the combination would be there. And I think this is the guy who just used math. No. So he calculated the confidence of the combinations with LightGBM. Number 5, I have a soft spot for because I kind of know this guy. He and I were in FastAI together, named guy named Radek. He is the FastAI library, and he said, oh, FastAI library was great because it was very flexible. He did something that was taught in the FastAI class, which was to start out with small images and then progressively get bigger. And this gives real speed advantages. This is how the FastAI team did so well on the Dawn Bench competition, if you remember. That happened 2 months ago or so. It was a competition to see who could train ImageNet the fastest. And the FastAI team did it in something like a half an hour or something like that. And so he could do his training really fast using some of the techniques that the FastAI groups have promulgated. And that meant he could do a lot of cycles. He's the one who blew up the is images to just the detected area. So he would detect an object first, and then he would crop and blow up the image to just the item, and then he would run it through an is detector to figure out if it was metal or if it was plastic or wood or fabric or whatever it was. He sent the images through a CNN and then sent the output plus the intersection of reunion, the relative distance, and the relative size to a model, another model. And then he scaled his predictions by appearance frequency. So he basically did statistics on the input data of the training set to figure out to adjust the probabilities in the test set. So this was his way of dealing with the unbalanced data. Submission number 7. I thought, I want to hire this guy or woman. I don't, yeah.
What kind of computational resources are they using? The
Radek?
Yeah, like estimation of computational resource.
I don't remember, but he's not rich. he's got some day job, they've been doing this on the side. I don't think his day job is machine learning, although I'm not sure about that. He did say what his computational resources were. I believe that he trained the whole thing in under 6 hours, but I don't remember the details. If you want, it's on Kaggle in this write-up. Actually, it might not all be on Kaggle. It might also be on the Fast AI forums. But if you search for Radek on the Fast AI forums, it's there's a congratulations on this show that comes up pretty fast. And that one gives some more details that are not in the Kaggle posting. So anyways, submission number 7, I want to hire this person because they were just cool. First thing was, they found a pre-trained model that would do detection. And that did detection, it was trained on the previous iteration of this contest, essentially. And so didn't have to do any training at all, just use that one. And then he just, or she, I don't know, they just used probability. They said, what's the problem, the probability that chair is at table is the probability that it's a chair, the probability times the probability that there's a table, and the probability based on the frequency from our training data, the probability that the chair is at the table. I wrote this wrong. But he just used, he didn't bother with anything else. He just used the probabilities from the training data. Do you have a question?
Yes, so how is this being handled if you have two chairs and two tables and one chair one table to another table?
The way I would do, I don't know how he did it, but the way I would do it is that I would do all of the combinations. Because as you saw, that you don't get penalized too much for that ones. Alexi wants the mic.
So why would that be? So let's say there is like chair and chair in two boxes, right? So probability of chair at chair would be like almost 0, so it would just go down, right? So you always compare two boxes, table, I don't know, table on table, like those are just the open probability.
Sure, but you also get here, you've got to get the wrong chair and wrong table, and wrong chair and wrong table, along with the replicating chairs and tables. You get two wrong, two right.
So there was like a feature in the very beginning, and one of the features was distance. So if you have a distance between two boxes, just use that.
Yeah, but I think this person didn't use distance. I think they just used the statistics from the test set and still got 7th place.
So what is that last probability supposed to be? It says chair table.
It's wrong. I wrote this down wrong. So, no, I know what it is. That's the probability that in the training set, if you have, what's the probability, if you have a chair and a table, what is the probability that it's chair and, that the chair is at the table? So if you have a chair in the picture and you have a table in the picture, what's the probability that the correct relationship is at?
Okay, so comparing at versus on versus
Yes.
after versus
Yeah.
interacts with.
Yeah.
Sorry, you may find it like a weird. I think you say you won't hire him or her because it's the method is very simple.
No, I want to hire.
Oh, you want?
Yes, because it's very simple.
Oh, okay, good.
Very, very simple. I mean, he or she did almost no work.
That's what I want, yeah.
And it's not the best, but you know, it's really fast. And then submission number 8, they merged item for the is. I think they did something similar to what number 4 did. They merged item and attribute to make 62 classes for the ises, and tuned on that. Use the Retton model in case you care. They didn't always say what kind of model they used, though pretty clearly they were always using, almost always using a neural network. And then this person just used scipy.minimize to calculate the weights, to calculate the confidence of the formula of weight 1 times confidence of item 1, meaning the confidence that this is an item 1, this is a cat. Weight 2 times the confidence of the item 2, this is a table. The weight 3 times the intersectional reunion, weight 4 times of 1 intersectional reunion item 2. Intersectional reunion relative to what the ground truth was. And W5 times the confidence in a relationship divided by the sum of all the weights. And it seemed to work reasonably well. Again, it looks like something relatively simple.
Sorry, can you quickly explain that intersectional reunion?
Sorry?
Can you quickly explain that intersectional reunion?
Sure. You've got 2 boxes. I have visual aids. Thank you. So you got two boxes, and they overlap. And plus, assistant, could you point to the place where they overlap, please?
The overlap.
So this would be the intersection.
The intersection.
The intersection, and now the union would be the sum of all of that. It would be. I don't think it's the big box. I think it's
It's hard.
Yes.
this one plus this one minus the overlap.
So sorry, what is 1 and 2 then? The intersectional reunions of what?
The training data includes information from them, ground truth, of what the box, where the box is supposed to be. So they think the box is supposed to be here. And you say that the box is here. You didn't do a very good job. So this is the first
Ground
one.
truth in yes
Yes.
versus item 1. And the ground truth in yes of item 2.
Item 2, yes. And that's what I got. Yes, Katie?
Yeah. You mentioned at the beginning that the main features that people used were the intersectional reunion, the absolute and relative distances between them, and the absolute and relative sizes.
Yes.
Were there any other features that anybody used besides those, or did anybody actually try analyzing the images themselves?
Oh, yes. They did analyze the images themselves frequently.
I mean, not just for classifications of the objects, but also for the classifications of the relationships.
It was hard to tell because some of them didn't say the product definitely did. So he detected the objects, and then he calculated all of this stuff, and then he fed the images through a neural net, took the output of that, and I don't know exactly what he means by that, but I'm guessing he meant the weights from the next to last layer. Took that and concatenated it all together and fed that into another neural net. There was someone else who implied that they did something similar, but these regs were all pretty terse. And so sometimes it was hard to tell exactly what they were doing. Yeah.
Sorry, I couldn't quite understand what's the difference between is and all of the other words? Like, why did they just, it's not very intuitive to me, like, why would you treat it differently and use a different algorithm?
Because is takes the adjective, whereas the others take an F. So with most of them, you have object, verb, object. With the is, you have object, verb, adjective. So you don't really have a second bounding box. You maybe have a bounding box for the one thing twice or something. And so that's why they're all treated them separately. Does that make sense?
Did the organizers explain why would they include that relation? Because it's obviously like, it's different from everything else, and as many people pointed out, you need to have the models to accommodate that, and it's like two different conditions, to be honest.
I have no idea why they did that.
It just doesn't make sense. Like from the first slide when you showed it, it's like relationship between two objects, and relationship, like, it's not a relationship actually, it's just a property of the object, right? Which is a separate problem. No, I mean, like, did anybody ask? No.
I don't think I've ever seen, I don't have a lot of experience, but I don't think I've ever seen the sponsor of a Kaggle competition say, oh, that's why we do that. It seems like once they throw it over the wall to Kaggle.com, it's like, your problem now. Even if there's problems with the data, a lot of times they don't already fix it.
Sorry, I just wanted to add that I think the reason to do the split might also be because it's a bigger chunk of the distribution of the total triplets. So I think I saw this, I think it is one of the most common combinations.
I think it's actually not.
Oh.
But I think I deleted the portion which had the different values with this, the different splits of the different relations.
One of the slides you were saying that there were like one of the answers made every is into a separate class. I guess it was like 42.
It's 42 or 64 or something like that. It was a small number.
And on the subject of splitting, it seems like every is case is going to, the object detection is going to happen at another level, right? Because your object detector is going to look at the material rather than the shape of the thing itself. So,
but I think you wouldn't have the, I think they had a separate neural net for figuring out the detection from the material. I'm not actually entirely sure of that.
but none of your other relationships are, none of your other tokens, like over, under, they don't need to know the material in this. Okay? So the two models are completely separately trained.
No.
Okay. Even at the object detection level.
I think so. One of the things about, maybe they used one model, I think, and I'm wrong. One thing about it is that if you, especially if you break it up into 62 classes, there's a whole bunch of things you don't have to detect. Like, you don't have to detect cats in that is thing, because cats are not made of plastic, leather, wood, or transparent. There are only about 6 different types of material. One of them is transparent, which isn't a material. But, cats are not ever transparent, so you just don't have to look for cats.
Not yet.
And so that would make your detection a whole lot easier. You only have to look for, I think it's 29 names instead of 100 or whatever.
But also like with whenever you have a neural net, it's like going into the neural net, you would just always just make that one model, right? So if you're training 2 different models, you're training completely from beginning to end, 2 different detection of the upper of those detection and just all yeah, the whole thing would be different.
So it's like you only train once? I didn't understand.
Well, if you have a detection algorithm that's a neural net, and then after that you have the relationship detection algorithm that's also a neural net, and you would just hook those up like together into one big neural net, so the error can go back through. And so if you're building a different model for the is relationship and the other relationships, then you're going to have a different detection algorithm, or you're going to have a different detection.
One thing I don't remember if I talked about or maybe I didn't emphasize is that many of the participants split off the is data for their training. So they took all the is data and sent it over there. They kept it out of the everything else data, so they split it out. But they took like 10% of, I don't remember, some fraction of the everything else data to use as negative examples in the is thing. But that meant that they had a lot more specialization of the training. They could get farther faster.
We're running close to the next one. Let's just have that ended here. Let's get Ducky.